Now let us see another important concept of this particular chapter, that is catalysis. So generally, if you see chemical reactions, as we discussed in chemical kinetics, all the reactions we come across, some of the reactions will occur slowly, some of the reactions will be moderate, and some of the reactions will be very slow. So here in this particular concept here, suppose you take a compound, that is KClO3, potassium chlorate. This potassium chlorate on heating, which dissociates into the corresponding products, potassium chloride and oxygen gas will be released. So here from this we can get the oxygen gas by the decomposition of the potassium chlorate. KClO3 is potassium chlorate. So on heating we can get two products here. One is potassium chloride, other one is the oxygen gas. And initially, suppose the reaction is carried, okay, and here it will take a large amount of the or higher temperatures in the range of about 623 to 873 Kelvin approximately. So simply can say these higher temperatures required. Suppose if the same reaction is carried in the presence of manganese dioxide, MnO2, reaction is same, but for that we are adding the manganese dioxide. So when we add the MnO2 to this mixture, so it is observed that the reaction is carried at the temperature lower than this, so approximately 400 to 600 range, so that we can get the products easily. That means in the absence of MnO2 we will require large temperatures, but in presence of the manganese dioxide, MnO2, it is observed the temperatures required is low temperatures as well as the reaction is enhanced. That means the reaction become faster to give the actual products. So that's why here in presence of the manganese dioxide, what exactly we have to understand here it is the rate of reaction has been increased. So all these kinds of the concepts were studied by the scientist called Berzelius. So that's why he called substance in presence of which the rate of reaction is enhanced, or as called as catalyst. So catalyst according to him, or in general way, so it is a substance which is added to the reaction mixture to fasten the rate of the reaction. And very important aspect that one has to remember here, it is the catalyst will never change its chemical composition. Will never change its chemical composition, as well as the quantity of the catalyst always remains same if you observe after the chemical reaction. So that's why the catalyst is a substance which do not change its chemical composition as well as its quantity is generally termed as catalyst. At the same time, it will enhance the chemical reaction rate. So those are generally called as catalyst. And the chemical reactions or the process which is enhanced in the presence of the catalyst are generally called as catalysis reactions. So what do you mean by catalysis? Means the chemical reactions which are enhanced or the rate of which is enhanced in presence of certain substances or the catalyst are called as catalysis reactions. So as we are aware, for example, in the manufacture of ammonia, just now I told you, we have to use finely divided iron as the catalyst. So here in presence of the iron, in the particular case, the rate of reaction becomes fastened so that the products will be formed with more speed. And at the same time, here one thing one has to remember that in presence of the certain substances, the rate of reaction can also be decreased. So that's why catalyst, we can say it is a substance which alters the rate. Here alters means it may increase the rate of reaction or it may decrease the rate of the reaction. So most of the cases, the role of the catalyst is to increase the rate of reaction. Of course, we have few cases or we have some cases where in presence of certain substances, the rate of reaction can be decreased. So that's why the catalyst, we can say it can be positive catalyst or it can be negative catalyst. So positive catalyst always enhances rate of the reaction, and the negative catalyst generally retards or decreases the rate of a chemical reaction. That's why they are called as the negative catalyst. Anyway, so most of the, in general, what is the role of the catalyst here? It will try to increase the rate of a chemical reaction. That's why we'll discuss mostly about the positive catalyst. Suppose if you come across about negative catalyst, we have the hydrogen peroxide, which is actually discussed in the hydrogenous compounds in the inorganic chemistry. Hydrogen peroxide H2O2, we have to take many precautions to store it, because H2O2 simply or easily decomposes into the corresponding products as water and oxygen. So that's why even at the normal temperature conditions also it can be easily decomposed. So that's why in order to prevent the decomposition of hydrogen peroxide, generally certain substances like acetonylide, urea, so these kind of the substances are added to the particular bottle where the hydrogen peroxide is stored, because in presence of those substances the decomposition of hydrogen peroxide is prevented, or we can say decreased. That's why the so-called urea, acetonylide, in this case we can call them as a negative catalyst. Of course, we can also use the word preservators. So in presence of this, generally the rate of reaction can be decreased. So we can simply they are stabilizers, or we can also call them negative catalyst. But anyway, most of the cases will discuss about the positive catalyst only. And before that, one should have an idea about certain aspects about the catalyst. So generally the catalyst will never initiate a chemical reaction. So what is the role of catalyst? Means it will increase or decrease the rate of reaction after the initiation. Suppose if a reaction is not at all started, if you add catalyst, nothing will happen. So that's why first of all the reaction must be initiated. So once the reaction is initiated, yes, so if you add the catalyst, it will alter the rate of the chemical reaction. So that's why the catalyst will never initiate the chemical reaction. It will alter the rate after the initiation. At the same time, very small amount of the catalyst is enough to convert large amounts of the reactants into the products. Suppose if you are using very small amount of the reactants, that doesn't mean that we have to use small quantity of the catalyst. If you use a large amount of the reactants, that doesn't mean we have to use a large amount of the catalyst. No, it's not required. So even the reactants are to large extent, we can use very small quantities of the catalyst is enough to alter the rate of a chemical reaction. At the same time, if you take about a chemical reaction, so here if it is a reversible reaction, for example, in the case of reversible reaction, suppose assume a forward reaction rate is increased by the addition of the corresponding catalyst. But in the reversible reaction, always definitely we can observe the attainment of the chemical equilibrium. So once the equilibrium is achieved or attained, so definitely there is no effect of presence or addition of the catalyst, because if the catalyst increases the rate of forward reaction, so automatically at equilibrium stage we are aware that the rate of forward and backward reaction will be always equal. So that's why, so what is the effect of catalyst at equilibrium? Means it has no effect. At the same time, suppose we are discussing about the positive catalyst here, we have added a positive catalyst. Exactly what happens? Of course, we have all discussed in the case of chemical kinetics here. Presence of the catalyst will alter the reaction path in such a way that it will choose the path where the activation energy is small or less. It will select the reaction path such that the activation energy will be less in particular path, so that the reactants are converted to the products easily or quickly. Okay. Apart from this, suppose I already told you we can use the positive catalyst or the negative catalyst as per the requirement. So there are some of the important aspects that one should have an idea about the characteristic properties of the catalyst. And apart from this, here there are two types of the catalysis or catalysis, that is based on the physical states of the reactants and the catalyst. So one is the homogeneous catalysis, the second one is heterogeneous catalysis. So what is the basis to classify like this? Here that is based on the physical states of what? The physical states of the catalyst and the reactants. If the physical state of the catalyst and the reactants are same, then it is called as the homogeneous catalysis reaction, or simply catalysis. If the physical states of the reactants and the catalyst is different, then it is called as heterogeneous catalysis. So just by comparing the physical state of the catalyst and the reactants, we can classify the particular catalysis into the two types, homogeneous as well as heterogeneous. So let us try to discuss all these with suitable examples. Take the first case, that is homogeneous catalysis. In the homogeneous catalysis, just now I told you, the physical states of the reactants and the catalyst will be same. For example, the hydrolysis of the ester. So here I am taking ester as ethyl acetate. Ethyl acetate in aqueous medium. The hydrolysis reaction with water. The products here will be, this is the water is a liquid, and H plus in aqueous medium. The products will be acetic acid and alcohol C2H5OH, which is the ethyl alcohol. So if you see, all are present in the same physical state. So here H plus is the catalyst. So that's why, as per this representation, in the hydrolysis of the ester in acidic medium, so here acid is used as a catalyst here. So in presence of this, we are getting the corresponding products as acid as well as the alcohol. So this particular reaction is an example for the homogeneous catalysis, because all the reactants and catalysts will be in the same physical state. And similarly, conversion of sulfur dioxide into sulfur trioxide in presence of the nitric oxide. So SO2 is gas, oxygen is gas, NO is also a gas, which is nitric oxide, NO. So here the reactants are gases, the catalyst also a gas. So here NO, nitric oxide, is the catalyst. So the physical states of the reactant as well as catalyst will be same in this case. So we can also take this as a homogeneous catalysis reaction. So here we can compare the respective cases. And whenever we come across about the homogeneous catalysis reaction, generally this will follow a method or mechanism, which is two-step mechanism. We can also call the mechanism as intermediate compound formation mechanism. Intermediate compound formation mechanism. For example, in the conversion of the sulfur dioxide gas, when it reacts with oxygen gas, we are getting sulfur trioxide gas in presence of the nitric oxide. So actually in the intermediate compound formation mechanism, first what happens is, in the first step, the catalyst will react with any one of the reactants to give some intermediate product. So in this example, in the first step, the catalyst is NO, nitric oxide. So this reacts with oxygen gas to give the corresponding product as NO2. So in the first step, what happens is, the catalyst will react with any one of the reactants to give corresponding intermediate product. Now this intermediate product in the second stage reacts with the remaining reactants to give the actual product with the release of the catalyst. So in the second step, in this example, so this is the intermediate product here. Now, so this will combine with sulfur dioxide to give the products as sulfur trioxide gas, and the catalyst is released. Here in the step 1, nitric oxide is the catalyst. Now this catalyst is reacting with any one of the reactants to give the intermediate product. So in this example, the nitric oxide is reacting with oxygen gas to give this as the intermediate product. Intermediate product. Now this intermediate product is reacting with remaining reactants to give actual product, which is SO3, as well as the catalyst is released here. Now this is the case how we can understand. So whenever if the process or the catalysis is homogeneous catalysis, so generally there occurs this mechanism. And coming to the second case, heterogeneous catalysis. So in this case, generally the physical states of the reactants and that of catalyst will be different physical states. For example, take nitrogen gas is reacting with hydrogen gas to give the ammonia gas. Of course, it is a reversible reaction. Here we use the finely divided iron as a catalyst. So physical state of reactants are gases, that of catalyst is a solid. So physical states are different here. The physical states are different here. And not only this, you can also come across about, of course, this is the Haber's process, the contact process, the conversion of sulfur dioxide into sulfur trioxide. This is also a reversible reaction. This can be carried in presence of the vanadium pentoxide, which is a solid. So physical state of reactants are gases, that of the catalyst is a solid. So this is generally the heterogeneous catalysis reaction. Not only this, we can also come across about the hydrogenation of oils. We call it as Vanaspati process. In the hydrogenation of oils, generally the oil reacts with the hydrogen gas in presence of the catalysts like platinum, ranitidine, or palladium. So in presence of this, we will get the corresponding fat. So oils are converted to fats here in the hydrogenation. So here the physical states of the reactants and the catalyst will be different. That also comes under the heterogeneous catalysis. Now, if it is heterogeneous catalysis, generally this will occur through the process or the mechanism which is called as, generally the adsorption phenomena is involved. So whenever we come across about heterogeneous catalysis, the phenomena involved here it is the adsorption. Just now I told you about the applications of the adsorption, in that we have discussed here. So whenever if it is the heterogeneous catalysis, Heterogeneous catalysis. The process is adsorption phenomena is involved. So basically here this involves various steps. In the first step of this process on the mechanism, the reactants molecules will accumulate onto the surface of the catalyst. The reactant molecules which are going to involve in the chemical reaction will accumulate onto the surface. We can also call it as diffuse onto the surface of the catalyst. This is the stage 1. In the first stage, the reactant molecules diffuse onto the surface of the catalyst. And second stage, what happens is the diffused molecules, they will get adsorbed on the solid surface. Once they get adsorbed in the second stage, the third stage, what happens is the corresponding adsorbed reactant molecules will combine to give the intermediate product. So here I mean to say intermediate means it is neither reactant nor the product. So once the intermediate product is formed on the surface of the catalyst, in the next step, fourth step, what happens is the particular product which is formed get dissolved. So once it is dissolved in the last step, fifth step, what happens is the corresponding product will be diffused out. So that means why exactly here all these kind of observed is nothing but the corresponding solid surface is having the vacant valencies. So these vacant valencies facilitate the corresponding reactants to accumulate onto the surface of the corresponding solid, as well as there occurs interaction between the solid surface as well as the reactants that leads to give the corresponding adsorption. If more than one different gases, otherwise the molecules are adsorbed, definitely the chemical reaction is observed on the corresponding surface. Now we will get there some intermediate product that finally convert into actual products here. Now those products will be get dissolved to give the actual products. Now the surface of the corresponding metal or solid will be ready for next adsorption by the reactant molecules. So from this we can understand that why only small amounts of the catalyst is enough. Because every time once the product is formed, again that get dissolved. Now that particular surface is readily available for the next adsorption followed by next reaction. The same we can show like this. Suppose assume I have a solid surface like this. This is solid surface. Now assume we have two reactant molecules that are A and B. So as per discussion I told you, first these two reactants will diffuse onto the corresponding surface. So assume they have diffused like this. So assume this is A is diffused on here, this is the B which is diffused here. So after diffusion they got completely adsorbed. So I am showing directly the A is adsorbed here and this B is adsorbed here. Now in the next step these two will form one intermediate product. So which is a substance which is neither reactant nor the product. So we can show the same thing like this. So A, this is B, you can observe the bond formation between this A and B. So this is intermediate. Now this intermediate finally changes into the actual product. Now again this is the catalyst, which is a solid catalyst. Now we got the product AB, or we can show like this also, same thing, A bond B. So actually here first the corresponding reactant get absorbed or accumulates or diffuses onto the surface of the solid. This is a solid catalyst, and once they got diffused onto the solid surface, now they will get adsorbed. So after the adsorption of the solid surface, they will form one product here. Of course, this is the intermediate stage. So this particular thing is not neither reactant nor the product. This finally converts into the actual product AB. Now this product AB will get diffused out. So once this AB is diffused out, now this particular solid is now ready, vacant, it is having with vacant valencies. So that's why we can continue the same reaction with the new reactant molecules. The reaction will proceed. Just I told you, this is the reason why we need very small amount of the catalyst is more than enough to carry the reaction with large amounts of the reactants. So definitely, so all these processes will be occurred continuously. So once we got the product, now this particular solid is having vacant valencies. So now this is ready for next adsorption followed by the chemical reaction to give the actual products. So in order to have all these cases, definitely there should be interaction between the reactants and the vacant valence of the solid. And very important thing is that this interaction should not be that much stronger. If it is very much stronger, it is very difficult to remove this AB from the solid surface, nothing but the catalyst surface. Attraction should be there, but it should not be that much stronger. So that if it is that much stronger, means it is difficult to remove AB from the solid surface or catalytic surface. If it is not removed, again it is not ready for the next adsorption followed by the next further chemical reaction. So this is the heterogeneous catalysis, and how the particular adsorption phenomena or the concept or the theory will explain about this particular process. Yeah. Now whenever you come across about the heterogeneous catalysis, many of the cases zeolites can be used as catalysts. Here zeolites are actually aluminum silicates, with three-dimensional structure, where actually they are having the complex or the polymeric forms of the silicates here, where in the silicate 3D structure some of the silicon atoms are replaced by aluminum. This facilitates the bond ALO silicon bond. And here these zeolites are having certain sites. So here these sites can be easily accommodated by the corresponding reactants. So here these kind of catalysis generally depends on the size of the corresponding pore of the zeolite which is having, at the same time the size of the reactant molecules or the shape of the reactant molecules. That's why these kind of catalysis is called as shape selective catalysis. So this is generally it is observed in the case of the zeolites. So they have some pores here. So those are actually because of the formation of the aluminum silicates here. So silicate structures have where some of the silicon atoms are replaced by the aluminum. So it is a polymeric kind of the structure here. So this will be having certain gaps or the pores. So in such a case, the particular catalysis depends on the pore size and also the shape of the corresponding reactant molecules. So these kind of catalysis we can call it as shape selective catalysis. Now let us see other process which is enzyme catalysis. enzyme catalysis. So actually enzymes are actually polymers. So these are organic polymers which are having the nitrogenous, so nitrogen. Okay, at the same time, so these are actually the proteins with heavier, high molar mass, molecular weight, and these have great role in live process, and they are generally called as the biochemical catalysts. Biochemical catalysts. So whenever we come across about the enzyme catalysis reaction, so basically that particular enzyme will react or will first form one intermediate compound with the reactant. Here we can call the reactant as substrate. So initially this enzyme with the substrate will form one intermediate which is called as enzyme substrate. Now this enzyme substrate finally changes or gives to enzyme actually the corresponding product or products. So it involves two steps here. This is the step 1, this is the step 2. The first step, enzyme with reactant which is substrate here, that will form one intermediate thing. So this intermediate finally changes into the enzyme and the product or the products will be formed. So here enzyme is acting as a catalyst now. Okay, at the same time, if you take any enzyme, this particular enzyme will be having certain active sites. So here the active sites will have or associates with certain groups like amino groups, NH2, or the acid groups like COOH, or alcoholic groups, OH groups, and also thioalcohol groups. So these are actually active sites which are associated with the enzyme. So these are actually responsible for this kind of the catalysis reaction to give rise to the actual products here. And generally the enzymes are enzyme reactions which are generally of course occurred in the plants as well as animals here. They have a great role, and the particular enzyme catalysis reactions are highly specific in nature. With the help of in presence of certain enzyme, we can expect or we can have only one kind of the particular catalysis reaction. The same enzyme cannot be used for further reaction which is occurred in the either animals or the plants. Highly specific in nature. And enzyme activity, if you come across, the enzyme catalysis reaction, the process can be generally occurred at a particular temperature. So in general, the process will be occurred about at 298 Kelvin to 310 Kelvin. And also the enzyme catalysis reaction are highly specific at particular pH ranges in between 5 to 7. So enzyme catalysis reactions are most predominant at the pH range of 5 to 7. So that's why the enzyme catalysis will be occurred under moderate conditions of temperature and also pH value. Okay. At the same time, the enzyme catalysis can be further activated or increased in presence of certain substances which are called as promoters. So what is a promoter means? The substance in presence of which the activity of the catalyst can be further increased is called as the promoter. And in general, the enzyme catalysis reactions are most efficient. So efficiency is very much higher in presence of the enzymes. So as I told you, the enzyme will be specific. So specifically one enzyme can be used for one kind of the particular reaction or the process. For example, if you take sugar, C12H22O11. This is nothing but sucrose. Sucrose, when it is hydrolyzed, reaction with water to give the corresponding products as glucose C6H12O6 and fructose C6H12O6. This is glucose This is fructose. This particular reaction generally occurred in presence of the invertage, the enzyme. So in presence of the invertage, so here the sugar is hydrolyzed to give the glucose and the fructose. So this is an enzyme. So reaction is catalyzed in presence of the invertage enzyme. We can also generally call it as inversion of the sugar. Inversion of the sugar that we discuss in the biomolecules there. Okay. Anyway, this is used particularly here. And also, if you have the starch is actually converted into the corresponding maltase. So in presence of the enzyme diastase, so that once we got that particular maltase, the same can be converted into the glucose. So that means here, if you take any particular reaction, the process which is in presence of the enzyme, so every particular reaction requires only one kind of the enzyme. The same cannot be used for different kind of the process or the reactions. That's why enzymes are generally highly specific in nature. The same enzyme cannot be used for different kind of the chemical reaction or the process in the life process. This is about different kinds of the catalysis process or the reaction. Sir.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.